So let me start by saying that the widespread development of sensors, data storage, and data acquisition devices has helped to make large data sets commonplace. It is predicted that in the future, every 2 years, the amount of available digital data will double. We are using different platforms to upload and collect the data. World Wide Web, digital libraries. We are using our cell phones to exchange data with each other. And also, there are more and more companies that are building heavily data-driven technologies. This data typically comes from different modalities. So you can have text data, you can have audio data, you can have images. Companies that are building AI-based platforms for autonomous driving will be interested in collecting also depth images and point clouds acquired by LiDARs, for example. And it is essential for the further expansion of AI technologies to, at the same time, build tools that can guarantee the safety of the system and detect the anomalous behavior of the system, where this anomaly can be caused by malfunction of the sensors or a failure of the system. Or some form of cyber attack, or simply a mismatch between the training and test environments, so the distributional shift. So all these aspects and challenges of the data motivated the following questions. First of all, how do we build AI approaches that scale favorably with the size of the data and that can be reused in many different settings in machine learning? Secondly, how do we perform information selection? So in particular, how can we identify the relevant modalities or relevant parts of the data and avoid wasteful computations associated with processing the irrelevant parts of the data? And finally, how do we verify and trust the data, and how can we detect the anomalous behavior of the system, especially in the setting where we are not necessarily interested in understanding the underlying phenomena that disturb the data driving the system in the first place? So I'm going to be providing some partial answers to these questions. And in the context of the first question, I will be discussing the extreme classification problem. So let me introduce the nomenclature first. By multi-class classification problem, I understand the problem where I give you a data instance, and this data instance is associated with one label chosen from a potentially very large label space. By multi-label classification problem, I understand the problem where I give you a data instance, and this data instance is associated with a subset of labels chosen from a potentially very large label space. So if I give you an image and I ask you to recognize one single face on that image, this is a multi-class classification problem. If I give you an image and I ask you to recognize all objects on that image, this is a multi-label classification problem. This type of problems find applications in building search engines, in targeted advertising, in the aggregation of online news stories and their categorization, recommendation systems, ranking system, and so on and so forth. And so we're interested in building good class predictor with logarithmic running time in the label complexity. So this particular plot is showing you the advantage of using logarithmic over linear running time approach. So you can see at million classes, the algorithm that runs in a logarithmic running time is 50,000 times faster than its linear counterpart. However, still, majority of algorithms these days for this type of problems run in the linear running time in the label complexity, including the one-against-all algorithm. So the reason we are interested in the logarithmic running time is because this is the best you can achieve given Shannon information theory. And the logarithmic running time naturally motivates the construction of the class predictor in the form of a decision tree. Constructing this decision tree is highly non-trivial because when making partitions of the data in every node of the tree, we need to take into consideration the properties of the feature space and the label space. And as we move from the root to the leaves, we would like to increasingly purify the label partitionings. And in particular, we would like to end up with pure leaves. So we would like to end up with leaves that correspond to mutually exclusive histograms. So those are label histograms. They are obtained by collecting the data points that reached particular leaf of the tree and then plotting the histogram of the labels. By mutually exclusive, I mean that the majority label in one histogram cannot correspond to the majority label of any other histogram of any other leaf in that tree. So let's try to design the objective function that will do partitionings in every node of the tree. So let's consider a particular node of the tree, and this node was reached by the following data points. I will consider a binary tree, so the partition effectively sends the example to the left child node and right child node. And I am showing two possible partitionings, the green one and the red one. So for the interest of the computational complexity, the fact that we want to have logarithmic depth trees, we would like to make balanced splits in every node of the tree, because it leads to efficient trees, efficient prediction. So here it is. I give you two balanced splits, the green one and the red one. But intuitively, the green one is more favorable. The green one is more favorable than the red one. The intuition behind it is as follows. So as you move from the root of the tree to the leaves, you would like the nodes to be exposed to increasingly simpler problems. The green split gives rise to simpler problem for children and old, the separation of two classes, whereas the red split gives rise to a more difficult task for children, the separation of three classes. So the notion of favoring the green splits over the red one is captured in the criterion that we refer to as purity. And so this is the objective function that we formulated. This objective function applies to trees of arbitrary arity M. So I'm trying to see how can I use the laser. Okay. So there is the first term. This is the balancing term. So the balancing term makes sure that we are sending the same number of examples to every child node of a particular node. We have a class integrity term that makes sure we never split data points of a particular class between children, but we can still send the entire class to more than one child node. So there's also a multi-way penalty term that penalizes sending examples to more than one direction too often. And so this is the objective function, the splitting criterion that we optimize, we minimize in every node of the tree to recover the data partitioning. This objective function enjoys very nice theoretical properties, so you can actually prove that decreasing this objective function leads to increasingly more pure and increasingly more balanced splits. Balanced splits naturally implies logarithmic depth trees and efficient prediction. And decreasing this objective function also leads to the reduction of the tree error. So you end up with the classification tree with a provably small error. There are also other properties of the objective function that I would like to mention. As you've seen before, the objective function extends to trees of arbitrary arity. The objective function can be easily optimized using stochastic gradient descent algorithm. Also, the objective function gives rise to the algorithm for tree construction and training that runs online. So this is wonderful for massive data sets, massive streams of data. The approach can be generalized to density estimation problem. In the density estimation problem, what you have to do, you have to estimate the probability of random variables given some context. So in some sense, this is a very similar problem to the classification problem. Then the objective function also can be used to simultaneously learn the class prediction and the feature representation. So let me explain more. So imagine I give you just a standard CNN model that consists of the convolutional part that extracts features from the data. And we have a fully connected part that predicts the class. The computational complexity of the operations run by the fully connected parts blow up if you have a large number of classes. So it is infeasible to then use this model, but we can get rid of the fully connected part of the network and replace it with a decision tree. So then at testing, I will push the input data point through the deep learning model to learn the feature representation, and then this feature representation is then pushed down the tree to predict a label or a set of labels for this particular data point. Training is a bit more tricky. So at training, I am pushing the data point down the deep learning model to extract a current feature representation of this data point, and then I'm pushing it down the tree. As I do it, I am accumulating the gradient of the objective function with respect to nodes that this data point hit. And then the accumulated gradient is backpropagated through the deep learning model to update the data representation. So as you can see, we can simultaneously learn the data representation and the class predictor at the same time. So here's a very, very small subset of the experimental results that we got. On the multi-label classification problem, I'm reporting the precisions for top 1, top 3, and top 5 classes. Also, the normalized discounted cumulative gain. This is a rank-sensitive score that takes into consideration the relevance of the classes. Our approach is called LDSM. This is a task of multi-label classifications with 200,000 classes. And as you can see, we show superiority over other commonly used multi-label classification approaches in the literature. In the next table, I'm trying to answer the following question, whether the fact that we are encouraging explicitly logarithmic depth trees directly translate into plausible prediction time. So I'm showing the prediction time for our method LDSM and other approaches in the literature which are not encouraging the balanceedness explicitly in their optimization problem. And as you can see, overall, we achieved the best prediction time. Okay, so far I've been focusing on the problem of developing AI-based approaches that scale favorably with the size of the data, and I will showing various applications of our decision tree-based approach that relies on a new objective function, and then I will focus on the remaining two problems that I mentioned in the very beginning of the talk, the information selection and safety. And from now until the end of the talk, I will be focusing on the autonomous car driving problem. So imagine I give you an autonomous car equipped with multiple sensors, for example, cameras and LiDAR, and I train this platform end-to-end, which means that my training data set consists of sensory inputs and the corresponding steering commands, and the steering command is the only available supervision. So I want to develop a deep learning framework where I will avoid fast increase of computational complexity as the number of my sensory devices increases. I would like to always activate only the feature extractors for relevant input and avoid any heavy computation done on irrelevant sensors. I also would like to avoid overfitting to the simplest and most informative sensor. So if I have an autonomous platform that is equipped with cameras and LiDAR, this platform most likely will overfit to the LiDAR information. And the reason for that is because those are low-resolution images that we obtain from LiDAR, and they directly contain depth information. So that means if you train your platform, then if you test it and your LiDAR becomes unavailable, the platform will crash. So we want to avoid that. We also want to guarantee real-time operation of the system, and we want to allow both discrete and continuous data selection. By continuous, I mean that I will be able to not only identify the useful modality or useful sensor for driving, but I will be able to extract the part of the data that are the most useful for driving. So this is the autonomous platform we have. It's a remote control car at scale 1 to 6, equipped with 3 cameras and LiDAR and Drive PX2 for computations. And this is the network that we would like to build. So there is a gating mechanism that takes as inputs 3 camera sensory registrations and also LiDAR input. For now, ignore that this LiDAR network is a bit complicated. And the output of this main gating network is a binary vector where 0 corresponds to the fact that the sensor is not relevant, and 1 corresponds to the fact that it is relevant. So let's say I just focus on selecting 1 sensor. So what I will do, the main gating network is then just activating the feature extractor that corresponds to the relevant sensor and deactivating all the other feature extractors. The extracted feature is then directly taken to predict the steering command. So main gating network is the bottleneck of the entire system, because intuitively it has to be a relatively large network to assess the usefulness of the sensors. And so the computational complexity will blow when we're going to have a lot of sensors, right? Because this gating mechanism is going to be larger and larger. And also this model cannot be trained end-to-end. We tried, it's very unstable. So we developed a training scheme that consists of stages. So look at the right side, the top right side. So in the first stage, we have a network that predicts the steering command based on all sensors, and the gating mechanism is embedded in this network. So in particular, the gating mechanism is in this green frame. The gating mechanism shares the feature extractors with the network for predicting the steering command. So the byproduct of the end-to-end training of this deep learning scheme is a distribution. So the output of this fully connected layer is a distribution that shows the relevance of the sensors. We can threshold this distribution and then move on to the next step, the bottom left step. So we now decouple the feature extractors of the gating mechanisms from the feature extractors of the actual network. And we will compress the size of the feature extractors of the gating mechanism. We train this gating mechanism end-to-end with the labels obtained in the first stage of training. And then the only thing that's left is to then plug it back to the actual final network, the bottom right, and then we are fine-tuning the entire model. So quite the same intuition is used to continuously select the most relevant part of the sensory input for driving. We applied it to LiDAR input. So now look at the top left part of the slide. So we took the LiDAR input and we divided it into 5 partially overlapping windows. We again trained the entire system end-to-end. The byproduct of this training is the distributions over the windows. That gives you an information which window is the most relevant for driving at a particular point in time. This distribution and the knowledge of the positions of the windows enable us to extract the optimal position of the window that is useful for driving. So if you look at the bottom right network, we applied it to the LiDAR. So we take the LiDAR input. We have a gating mechanism that crops the LiDAR input to focus on the part of the LiDAR input that is the most relevant for driving. And then this is fed to the main gating mechanism. So here is the comparison of our approach, the last 2 rows, with other approaches. The first 3 are the networks that are relying on only one sensor. The next 3 approaches are the networks that are relying on more than one sensor. We are comparing the computational complexity in terms of the number of floating point operations. So you can see that our network has computational complexity comparable with the single sensor networks, but it actually uses all sensors for driving, while at the same time it's significantly better than the networks that are using more sensors for driving. And now if I can ask for the first video. Okay. So this is how it works in practice. We're going to see in a second. Okay, so in this case, we have a LiDAR and 3 cameras enabled. So as you can see, the network will rely on the LiDAR information, and it will select the part of the LiDAR information that is the most relevant for driving. And then if the LiDAR is disabled, the network did not overfit to the LiDAR, so it is doing perfectly well, relying on the cameras. And now what we are doing, we are shutting off parts of the LiDAR to show you that we can flexibly, in real time, switch between the LiDAR and the camera modality. So for example, if you turn left, if the left part of the LiDAR is active, then we will select that one. If it's disabled, then the network will switch to relying on the left camera. Okay, so let me move on to the last part of my talk, the problem of safety in autonomous driving. I'm going to be now focusing on a case where I have an autonomous robotic platform, and for the simplicity, let's say I just drive it based on one camera input. And I would like to develop an online monitoring framework that validates the behavior of the system. So in particular, I want to monitor the validity of the mapping from sensor inputs to actuator commands. In other words, I want to understand whether the steering command that the autonomous platform is following is well matched with the actual sensory registrations. So for that, we modified the generative adversarial network. We are using conditional energy-based generative adversarial networks. We have a generator and a discriminator, where the generator learns to convert the prior distribution to the distribution of the steering commands conditioned on the sensory registrations, and the discriminator that validates the quality of the mapping learned by the generator. So based on the conditional input, the discriminator is evaluating whether the steering command predicted by the generator is the right steering command. Okay, so let's look at how it works in practice. In the top, you have a normal behavior of the autonomous platform. In the bottom, you have abnormal behavior of the autonomous platform. Some of the images comes from the robotic platform that we have. There is also on the top right, there is also the images from the Udacity dataset. And in the bottom rows, for each image, we are showing the output of the discriminator as a function of a steering command with the corresponding image in the top row as condition. So the optimum of the discriminator curves is the optimal steering command that the discriminator thinks fits best to the actual image, whereas this red dot is the actual steering command that the autonomous platform is following. So as you can see in the top part of this slide, the optimum of the discriminator curves is well matched with the actual steering command that the autonomous platform is following, where in case of the anomalous behavior, so this is this bottom part, so on the left side you have I believe, late right turn, and on the right side you have early left turn. What is happening is you can see that there is a mismatch, eventually a mismatch between the optimum of the discriminator curves and the actual steering command that the autonomous platform is following. So we really don't care what caused the autonomous platform to misbehave. We just care to detect that, okay? So let's look at the simulation. So in this simulation, the negative steering commands correspond to turning right. So we have discriminator curves and the steering command that the platform is following. This is a normal behavior. The blue curve is the location of the optimum of the discriminator curves. The red curve is the steering command that the autonomous platform is actually following. So this is a normal behavior, so it means that the optimum of the discriminator curve will be well matched with the actual steering command that the autonomous platform is following, whereas in this case, we will see the anomalous behavior. So in a second, my student will turn to the wall. You see, and there's increasing mismatch between the optimum and the actual steering command, and one more video showing the abnormal behavior. So you see there is a mismatch now between the optimum of the discriminator and the actual steering command that the platform is following. Okay, so if we can go back to the slides, perfect. So let me just quickly summarize. I showed you how I proposed some approaches for scaling AI-based approaches to a large data setting. It is based on decision trees with a new objective function, and it's applied to multi-class, multi-label classification problem, density estimation problem, problem of learning feature representation as well. I discussed the problem of information selection using reconfigurable networks to select relevant data, and I was talking about monitoring the safety of data-driven AI-based systems based on the generative adversarial networks. I have no time to talk about future directions. I can talk offline. The papers related to this works at ICML, NIPSIS, and NICRAS and IROSys can be found on my website. And I would like to give special thanks to my wonderful group. This is a team of very bright, young people. Mariam Maizupi, who is working on the multi-class classification problem, and she is doing both of the experiments, and also she is deriving the theoretical guarantees. Shihong Fang, my student, who has built himself our robotic platform. He has been programming on DrivePX2, so kudos for that. And he has been working on the problem of information selection. Apurva Nandini Saridena, who is consistently fighting with generative adversarial networks, forcing them to work to monitor the safety of our autonomous driving system. And also Yunfei Tang and Devansh Bisla, they have not been participating in this particular research, but they've been discussing with us. So this is, I'm very privileged to work with these people, great kids. And finally, many thanks for NVIDIA, for the autonomous driving team in New Jersey, especially to Urs Muller, to Larry Jekyll, to Mariusz Bojarski for working with us, for having wonderful research collaboration this past 2 years, and also for giving DrivePX2 to my lab. And finally, in this last 20 seconds, I just want to emphasize that I'm also an organizer of the NYU Tandon EC seminar series on modern artificial intelligence in NYU Tandon. The talks are live streamed. The talks are available on YouTube. And also, the doors are open for everybody. So even though we ask for registration, we never check that. So anybody from New York, from New Jersey, or from California, or from Singapore, and so on, can come and join us for this talk. We have wonderful line of speakers. Some are Turing Award winners, right? Nobel Prize winners also, and we have wonderful speakers confirmed for the future. So please come. Thank you. And I'm going to take, I guess, questions offline. Thank you so much.